If you take a pen and draw a continuous loop on a piece of paper, you divide that page into two distinct areas. You have the space trapped inside the line and the space left on the outside. To anyone looking at it, this is a completely obvious observation. It feels so intuitive that trying to mathematically prove it seems like a waste of time. But we run into a problem when we stop drawing smooth, simple loops and start pushing the limits of continuity. A curve doesn't have to be a neat circle. It can be infinitely jagged, folding in on itself to create a dense, space-filling fractal where the boundary becomes visually impossible to track. When the shape reaches that level of complexity, human vision fails. We can no longer tell just by looking whether a specific point is trapped on the inside or floating on the outside. Our geometric intuition breaks down completely. To guarantee those two separate regions actually exist, we have to abandon our reliance on shapes and use the rigorous, abstract framework of the Jordan Curve Theorem. The standard textbook for building this mathematical foundation is James Munkres Topology. If we open it to Chapter 10, Section 63, we find the formal statement and proof of the Jordan Curve Theorem. To understand the proof, we have to leave standard geometry behind. In topology, we do not care about distance, angles, or whether a line is perfectly straight. The only properties that matter are those that survive continuous deformation, stretching, twisting, and bending without tearing. This means we have to stop analyzing the curve as a static physical shape drawn on a page and instead define it as a continuous mathematical mapping. This diagram shows our foundational building block, the standard unit circle, known as S1, centered on a coordinate plane. In topology, a homeomorphism is a specific kind of function. It is a bijective, continuous mapping that also has a continuous inverse. We use a homeomorphism to pull points from our perfect unit circle and stretch them across the plane, mapping them into a new, irregular, non-circular loop that we will call C. This gives us our formal definition. A simple closed curve is any subspace of the plane that is homeomorphic to S1. Because the mapping is bijective, this tracing path is guaranteed to be continuous, and it will never cross over itself. Once the curve is defined, our focus shifts to the remaining space. We want to study the properties of the subset of the plane that is left over when we remove the curve C entirely. By defining the curve through a homeomorphism, we take any wildly complex shape and tightly anchor its topological properties to the predictable math of a simple circle. This brings us to the formal statement of the Jordan Curve Theorem. It states, if C is a simple closed curve in R2, then the space remaining outside of C has exactly two connected components. The first thing to notice is the strict limitation. The theorem mathematically guarantees there are exactly two disjoint regions, never one and never three. This visual illustrates the first component, the interior. It is topologically bounded, meaning we can draw a larger finite circle that completely encloses the entire region. The second component is the exterior. Unlike the inside, this region is strictly unbounded, stretching infinitely in all directions. The final requirement of the theorem is that the curve C acts as the exact topological boundary for both of these components at the exact same time. The theorem strips away the need for visual confirmation. It forces a strict binary split of the infinite plane, mathematically mandating that an inside and an outside exist, no matter how chaotic the boundary gets. To prove this actually happens, Munkres begins his framework by analyzing an open curve, which mathematicians call an arc. An arc is defined as a space that is homeomorphic to a closed interval from 0 to 1. This animation shows the foundational lemma. An arc does not separate the plane. We can take a dotted line and trace a path freely from one side of the arc, around the open endpoint, all the way to the other side. Because we can complete that journey without intersecting the arc, the remaining space is still just a single continuous component. Watch what happens when we join the two endpoints to form our loop. The instant they connect, the previous path is severed. By closing the interval, we destroy the single component, forcefully separating the plane. This relies on a concept called path connectedness. To prove any 2 points exist in the same component, you must be able to draw a continuous path between them that never crosses the curve. Once the loop is sealed, any path attempting to travel from a point in the bounded interior to a point in the unbounded exterior is guaranteed to intersect C. An open interval allows traversal. Closing the loop severs path connectedness. That severed connection is the proof that the plane has been split in two. This diagram displays the ray casting algorithm, which helps explain why the topological proof is necessary. If we cast a straight line outward from a point inside a complex polygon, we can count the boundary intersections. An odd number of intersections means your starting point was inside. This algorithm works flawlessly for polygons because we can easily count the discrete times the line crosses the boundary. But watch what happens when we test this algorithm against a continuous but nowhere differentiable curve, like a fractal. If you try to cast a straight ray through this jagged boundary, it will intersect the line infinitely many times. It becomes mathematically impossible to calculate whether the total count is even or odd. When a shape approaches infinite complexity, computational geometry hits a dead end. The only way to rigorously prove separation is by relying on the topological invariant, the homeomorphism linking the curve back to a simple circle. Let's bring back our highly complex, visually indistinguishable curve. Thanks to the Jordan Curve Theorem, we don't have to guess. We know for a fact that there is a distinct interior region. Topological rigor provides certainty exactly where our visual intuition collapses. This proof is a mandatory foundation for advanced mathematics. You cannot execute complex analysis, like Cauchy's integral theorem, without first guaranteeing that your closed contours define an interior space. It is similarly required in graph theory to verify the properties and boundaries of planar graphs. The Jordan Curve Theorem takes what seems like a childlike observation about a drawn loop and transforms it into a load-bearing pillar for higher mathematics. To study the deep logic that builds this proof, you can look to Munkres topology. You will need to start with the foundational separation axioms and the Urisohn lemma outlined here in Chapter 4. Mastering these foundational steps is how you successfully transition from standard calculus into the abstraction of real topology. If you want to continue breaking down the logic behind higher-level mathematics, make sure to subscribe to the channel. Sometimes in mathematics, it is the most obvious visual truths that require the most profound logical proofs. Thanks for watching.